Hello everyone, and welcome to 11.4 of Chapter 11, and we've been learning about gases. So in this lesson we're going to cover Charles' law, and in Charles' law we're now going to take temperature into the equation because we know from the beginning that temperature has a direct relationship on the volume of a gas. We're going to look at temperature in terms of Kelvin this time. And Kelvin is a scale that runs from 0 to 273. And remember, we don't say degrees, so that's going to be kind of hard to break because we're so accustomed to saying degrees Celsius or degrees Fahrenheit. We're just going to say 100 Kelvin and leave it at that. Our constants in these equations are going to be pressure and the amount. So we're going to see P and N stay the same. And then when we increase the temperature of a gas, we're going to see the volume increasing. And when we decrease the temperature of the gas, we're going to see that volume decrease. So let's take a look at this graphic over here. We've seen a couple of them. And again, if we lower that piston and we increase the temperature, or we decrease the temperature, excuse me, and let's say the temperature is at 200 Kelvin and we've got 1 liter in here, we can see how the gas molecules are moving and exerting pressure at all different angles here. When we increase that temperature to 400 degrees, or 400 Kelvin, we can see that expands the volume to 2 liters. So you can see the direct relationship here that as temperature increases, the volume increases. Okay? Alright, so let's take a look at the formula that we're going to use for this. And just like we did with Boyle's law, we had what our initial is going to be to what our change is going to be. So for Charles' law, it is written, the formula is V1 divided by T1 equals V2 divided by T2. Remembering we don't have to worry about pressure and the amount because that's constant, so we're only going to look at volume and temperature. So let's say that we needed to solve for V2. So we've got to do a little bit of rearranging of our equation and we've got to get V2 by itself. So the easiest way to get V2 by itself is to take T2 and multiply that by bring it up and multiply it by T2. This now allows us to cancel out the T2. And we need to remember that whatever we do to this side of the equation, we need to do to this side of the equation. So we're going to bring T2 up over here and get T2 times V1 divided by, so simply we're going to be saying V2 is equal to V1 times T2 divided by T1. Okay, so that's how we can rearrange Charles' law to solve for V2. Let's see how we can put Charles' law into action. A balloon has a volume of 785 milliliters at 21 degrees Celsius. If the temperature drops to 0 degrees Celsius, what is the new volume of the balloon? And keeping in mind that pressure is going to be constant. So the very first thing that we need to do is we know that Charles' law needs to be solved in Kelvin. So we have to change 21 degrees Celsius to Kelvin. And changing to Kelvin is really easy. You're just adding. So you're going to take 21 degrees Celsius and you're going to add 273 Kelvin, and that is going to equal 294 degrees Kelvin, or there I go, Kelvin, no degrees, just Kelvin. And now we need to change 0 degrees Celsius to Kelvin as well. So 0 degrees Celsius plus 273 Kelvin is going to equal 273 Kelvin. Easy. Now, what we're looking for is we have a volume of 785 milliliters, and we want to know what the new volume is going to be. So our new volume is the volume of change, so this is V2. Just like we learned in the previous screen, we've got to get V2 by itself. So V2 is going to be equal to V1 times T2 divided by T1. So easy, we're going to do just a little bit of multiplication and division. We're going to take our volume, 785 milliliters, times our temperature in degrees Kelvin, which is going to be, our T2 is the temperature after the change, and that's going to be 0 degrees Celsius. So that's 273 Kelvin from what we figured out over here. And we're going to divide that by our T1, which is 294 Kelvin, and that's going to give us, cancel out our kelvins, that's going to give us 729 milliliters. Not too hard, right? Good, I'm glad you're getting this. What this problem shows us right here is when the temperature decreases, the volume decreases. Did our volume go down from our original volume over here? Yes, it did. It did go down. And that's what we're looking for when we're looking at Charles' law, is that temperature, as the temperature decreases, is that volume decreasing as well. All right, so now with this problem, we're going to do this problem in two ways. We're going to look at it where we're going to do three major steps, a lot of work. And then the next one we're going to look at it doing it a little bit easier way than this. But I want to show you that there's two ways of doing this. And because we're going to be looking at a different way of doing it, we're not going to worry about changing to Kelvin. We're going to keep it in degrees Celsius. So here's our problem. A sample of oxygen gas has a volume of 420 milliliters at a temperature of 18 degrees Celsius. So we want to know at what temperature in degrees Celsius will the volume of the oxygen be at 640 milliliters. So we know the initial volume, we know the initial temperature, we know the final volume, the volume in change. What we're going to be looking for is the T2. So that means we've got to get T2 by itself. And the first way that we're going to do that is very much like what we did in the previous equation. We're going to take T2 and we're going to multiply it by V2 so that we can cancel out T2 and get V2 alone. So remember, whatever we do to this side of the equation, we have to do to this side of the equation. So that means we're going to have to take T2 times V1 divided by T1. So this is what our end result is going to look like. We're going to get T2 times V1 over T1 is going to equal V2. Not too hard. Now we've got to get this T2 alone that's over here, and we're going to do much the same thing. In order to get T2 alone, we've got to get rid of V1. And the way we get rid of V1 is by dividing this side by V1 so that the V1s cancel out. And then whatever we do here, we've got to do over here. So we've got to bring V1 under the V2. So essentially what we're getting is this T2 by itself, the T1 here, and we have V2 over V1. Now, what we need to do again is to get this T2 alone. So in order to get this T2 alone, we're going to take the T1 and remove the T1. So in order to do that, we're going to put the T1 in this blank space that we left here. So T1 divided by T1, they can cancel out. Whatever we did to this side, we have to do to this side. So that means we have to bring T1 over here and multiply it. And what we're going to get is, for our formula, we're going to get T2 equals V2 times T1 divided by V1. All right, this is the formula that we're going to have to work with. So we had to do a lot of steps in order to get to this formula, but let's see an easier way. Okay, so you guys are probably familiar with the crisscross. So we're just going to crisscross things. Here's our original equation. We've got to get T2 by itself. So the very first thing that we're going to do is we're going to crisscross the V1 and the T2. So when we do this, we're going to just bring V1 down, and we can eliminate our V1 with that. We're going to bring our T2 up with that. And then we're going to bring our T1 over here. Just going to bring that T1 up to there. And now we have our equation. We got T2 equals V2 times T1 over V1. So that's a little bit easier than all of those steps. Again, we're just crisscrossing. We're bringing the V1 down. Bring that V1 down. And in the exchange, we're going to put the T2 up. And then over here, we're going to bring the T1 up, and we've got our equation. And then over on the side, look what I've done. I've set up here. I've set up what we know within the equation, just like we've done before in other equations. So I put my V1 equals 420 milliliters, my T1 equals 18 degrees Celsius, my V2 equals 640 milliliters, or 640 milliliters, and I'm looking to solve for my T2. I can, if I want to change this over to Kelvin, which we can do, is we can take 18 degrees Celsius plus 273 degrees Kelvin, and we're going to put 291 Kelvin. And we do. We want to change that over to Kelvin all the time. And that's just an easy fix. So when we put this into our equation, we're going to put 640 milliliters. All right, that is going to be our volume 2. We're going to put 291 Kelvin. That's going to be our temperature 1. And then our volume 1 was 420 milliliters. And when we put that in, we are going to get, for our answer, 443.43 Kelvin. Okay, so what does this show us? What are we seeing here with our temperature and our volume? Are we seeing that our temperature in degrees Kelvin goes up or goes down when we have a change in volume? When we go from 420 milliliters to 640, what does that mean? Is our temperature going up or is it going down? Let's take a look. It's 443.43 Kelvin. That's a lot higher than 291 Kelvin. Wouldn't you agree? So again, this shows the relationship that as volume goes up, the temperature has to go up. So we see that direct relationship with that. Alright, so the last two slides that you're going to see here are going to be problems that you are going to solve as practice problems and turn in. So helium gas is used to inflate the abdomen during laparoscopic surgery. A sample of helium gas has the volume of 5.40 liters and a temperature of 15 degrees Celsius. We need to know what is the final volume, and we're going to do this in liters, of the gas after the temperature has been increased to 42 degrees Celsius at a constant pressure and amount of gas. Alright, so here's what I want you to do. I want you to show me the equation that you're going to use and how you change that equation to answer the final volume. I want you to show me how to change degrees Celsius to Kelvin, and then I want you to show me the work, and then I want you to tell me what that means about the relationship between the temperature and the volume. Okay?